4.2 logarithmic functions. Okay, so what's the logarithmic functions? So in a view of function, logarithmic function is inverse function of exponential function. Keep in mind this. Okay, and then in a view of algebra, the logarithmic function, the logarithmic function in the log is called, normally we say just log, okay? Log represent the exponent in our exponential function. What that means, think about this, y is equal to e to the x. Okay, this is, now we know what it is. This is exponential function, right? Okay, so now then we could isolate x. How can I isolate x? Okay, so think about this. I want to find out the inverse function using a switch and solve method. Remember the switch and solve method? So we use the switch and solve method to find out inverse function, right? In our chapter 2. In that, in there, using the try to find the inverse function using switch and solve method, then we have to interchange x and y, right? X is equal to e to the y. That's, I think, step 2, right? Step 1 is to replace f of x by y. Now step 3, and then what? We need to solve the equation for y. Here's the question: how can you isolate y? That's a big problem, right? Let's see. So to isolate y, then well, what are we gonna do? So there's no way to isolate y, right, in here. Okay. So actually, then y represent x, right? Because we just interchange x and y, right? So now back to this one here. So now let's figure out how to isolate y, isolate x. Now there's no way, right? So the mathematicians define the U symbol. So log means log, okay? And then y, and then to the base e. We say, they say this is represent x. Okay, so the schema is base goes to the bottom of the symbol log, and the y goes to the other side, x goes to the left side. Okay, so in general, y is equal to a to the x. And by the way, what is e? Natural number. Okay, this is a specific example. So in general, x goes to the what here? The x goes to the other side, right here. Okay. And then a goes there is equal sign and the log right there. Okay. And the log and the a base goes to the top, bottom. I'm sorry, it's bottom. Okay, right here. Okay. And then y goes the other side. Oops, let's show you this, right? Goes the other side. Y. Okay, so keep in mind this. Right. So now we reduce this one as log of y with the base a or to the base a. Okay, keep in mind this. All right, so now since we got this one from the exponential functions, so the a must satisfy the conditions in the exponential, what we define the exponential function, which means the a must be greater than 1 and a greater than 0. Oops, sorry, the a is not equal to 1. Okay, keep in mind this. Okay, so and then this is the example. I know, so it's a little bit, this is a little bit complicated, right? This is a more specific example. Think about this. Let's see, 49 is equal to 7 squared, right? So now here we could express the exponent 2 in terms of 7 and 49 using the log symbol, okay? So 2 is equal to log of 49 to the base 7, okay? So now if you now it's still, this is really, you know, abstract, right? It looks like a really abstract. So, but it's but keep in mind this is a number, okay? So if you have a calculator, so you can calculate this one, okay? Then definitely your calculator will return to number 2. Okay. So the other one, okay, so think about this. The 1/25 is equal to 5 to the negative 2. Is that 5 to the negative second power is 1/25, right? The negative 2 is equal to what? Log of 1/25 to the base 5. Okay, keep in mind this. So now, see. So here's our objective. Okay. First, we gonna study definition, but yeah, we already see the definition of logarithmic function, right? Let's say, let me just say log, okay? And then we see a graph of log, okay? And then properties of log, and then the fourth one we see the common log, natural log, and natural log. Okay, for 5, we're gonna study laws of logarithm. Okay, maybe I'm gonna introduce one the first. Okay, this is quite important. Okay, so then 6, yeah, we're gonna study how to solve the equation involving log. Okay, so this is one-to-one property of log. Okay, and 7. Okay, then we see, yeah, and then with the logarithmic family of functions. Okay, so how can you plot the graph of log functions using the transformations? Okay, so when I'll cover this one, when I'm gonna cover that one when I cover the graph of log. Okay, so first one, yeah, we saw definition, right? Okay, so now let's figure out the graph. Okay, let's see. So as what we did in exponential function, we're gonna think about 2 cases. Okay. Oops. Case 1, a is between 0 and 1. Okay. In case 2 is a is greater than 1. Okay. So now I told you what the logarithmic function is inverse function of what exponential function. Okay. So we're gonna plot the graph of the exponential function with base a, which is between 0 and 1. So graph must be like this. Okay. Let's say this is a graph of exponential function a to the x. Okay. All right. Then now I want to plot the graph of logarithmic function, which is inverse function of this. Okay. Then we learned that if 2 functions are inverse each other, then then their graph must be reflection. I mean symmetry about the y equals x. Okay. So let me plot the y equals x. So this is y equals x. Okay. This is y equals x. Okay. And now I'm going to, well, by the way, this is a graph of the exponential function a to the x, and then a is less than a is between 0 and 1. Then the reflecting the graph about the y equals x. Okay. Then we got this. Okay. So that's the graph of log function. So this is graph of log of x to the base a. Here a is between 0 and 1. Okay. This is inverse function. Okay. So the key mind is here f inverse of x. This is represent what? X. in the exponential function. Okay. And then that f of x, actually y value of exponential function, represent what? The x in a log function. That's the relationship between a function and its inverse function, right? Okay. So now, keep in mind this is a graph of the log function to the base a, and the a is between 0 and 1. And then you can see that that log function doesn't have what y-intercept because the graph never touched y-axis. Okay. So, second, let's see. Then the x-intercept gonna be, you see that here, exponential functions has a y-intercept, what, 0, 1. Okay, since the two graphs are what symmetric about the y equals line y equals x, then what that point, coordinate this point must be what 1, 0, right? Okay, and then you may wonder that why does this curve, the graph of log function never touch y-axis? Because you see, think about this. Let me see. Y is equal to a to the x, okay, and the x is equal to log of a to the base log of y to the base b, okay. So then for any choice of x, y cannot be 0, right? For any choice of x, y cannot be 0. It means that in the view of log, that y cannot be 0. That's why x cannot be 0 in the view of log. So the graph never touches y-axis. In order to that the graph touch y-axis, then what it should exist corresponding, y will corresponding to x equals 0, but that x cannot be 0 because of, see here, y cannot be 0. Okay, so keep in mind this. So or you can say that you see here in the exponential function, you see the y cannot be 0 because the graph never touch x-axis. It means that y cannot be 0. Then its inverse function, log function, x cannot be 0. Okay, either one is fine. Okay, so now next one, case 2. So what about a is greater than 1? Okay, so then we start from the graph of exponential function like this. This is graph of f of x. This is a to the x. Okay, and then I'll draw the y equals x like this. Okay, and then let me draw the graph with blue. Okay, then I'm gonna reflect the graph about y equals x. Then we're gonna get this. Okay, so this is graph of f inverse. This is a log of x to the base a. Okay, so this is definitely just going to be 1, 0. Okay, that's the 0, 1. Okay, so as you can see that here, if base a between 0 and 1, the graph is decreased function. If a is greater than 1, this is increased function. Okay, and then what range of domain for both cases? Range going to be negative infinity to infinity. Domain must be 0 to infinity. It makes sense because in a domain range of exponential function must be range of log function. The range of exponential function must be domain of log function, right? So keep in mind this. Okay. So now next one. So we figured out the graph and the properties of log, right? So then what about the log? Okay. So it's quite important. Okay. Well, let me introduce common log and the natural log. Common log and natural log. Okay. So if this specifically if the base is 10, okay, of x, okay, that one is can be written as just log of x. Okay, if you got problems about logarithmic functions and then you don't see the base in the bottom, okay, that means this is log with base 10. Okay, and then that is called the common log. Okay, common log. Okay, common log means that a log of x, the log with base 10. Okay, and the other one, what about the if the base is e, natural number, then can be written as just ln x. Okay, ln is a natural log. It means the log with the base e. Okay, that's called the natural log. Okay, so to keep in mind these two special logarithmic functions. Okay, so now laws of log. So laws. This is laws of log. Okay. So first one is this log of what a, okay, x to the what n's power is equal to n times log of x to the base a. Okay. So if you see the exponent right there in this number, then n can be brought out in front of log. Okay. The second one, log of a to the base a. If that number was same as the base, this is 1. Okay, keep in mind this. And then third one, log of 1 to the base a. This is 0. Okay. All right. So the easy way to memorize this, I told you the log represent exponent, right? So exponent of what? Exponent of the base a. So a to the 0th power is 1. Makes sense, right? And the a to the first power is a. Makes sense, right? Okay. Then the next one is this. There are many laws of logarithmic, but I think you just memorize these 3 is enough, I think, in this class, in this course. Okay, so now let's see the examples. Okay, so give me a second. Let's see example 2 in textbook. Okay, it's a simple problems. So just calculate log of 1000. Okay, so how can you do that? This is you see that this is common log. Why? Because the base is not indicated, so that should be common log. Now this is equal to log of 10 to the third power. Because 1010 to the third power. Then I'm going to use the property number 1. I mean law number 1. Okay. So then this is equal to what? 3 times log of 10. Since this is a common law, which means the base is 10. By the second law, that log of 10 must be 1. So we got 3. Or you can figure out this the answer by doing like this. Just set y is equal to log of 1000. Okay. So then let me just put the 10. Okay. And then I'm gonna rewrite this one as exponential expressions. It means that 10 to the y power is equal to 1000, right? Okay. Let me tell you this. You should be really familiar with to back and forth, converting, rewriting log expressions, exponential expression to log expressions. You should know this, okay? So you should know how to, rewriting log to exponential log, okay? So now you can see that here, y must be what? 3, right? Because 10 to the third power is 1000. Either one just fine, okay? Using the log to get 3, or just rewriting the log expression, and then just figure out the exponent, okay? So that's the A, and then B. And what about the natural log of -6? Okay, so natural log of -6, this is equal to means what that is. I don't think we can figure out by hand. Okay, because natural log means a log of -6 to the base e, right? Okay. In this case, we use a calculator. So if you have TI calculator, then you can figure out this. So open, just turn on the calculator. You see the what right here. See, you see the ln right there. So I just put ln, and then -6. Then you get the number. Oh, yeah. Yeah, we got the error right here because you see that the, let's see, right here, because the x must be what? Between 0 and 1, right? Remember that? So f of x is equal to log of x to the base a. A must be greater than 0 and the a is not equal to 1. And then domain is what? We saw that domain must be what? The 0 to infinity, right? Because the -6 is not on the in the domain. Okay, so that the answer is what? Yeah, just d any does not exist. Okay, so this, or you can say undefined. So d does not exist or undefined. Okay, either one just fine. Okay, it makes sense. You're just saying that y is equal to natural log of -6. It means that e to the y is equal to -6. But e is what? E 2.7 something, right? 2.718 something, okay? So then what? Then e positive number to the some exponent equals negative number. There's no such a y. There's no such exponent. Okay. Now let's see. Let's see. Yeah, let's see example 5. Next one. Oh, give me a second. Yeah, so one-to-one prefer, yeah, let's see one-to-one property of log. Yeah, I forgot to explain about this. So now this is example 6. Example 6. Let me explain one-to-one property of log by solving example 6. Okay, so one-to-one property of log is this. If log of x1 to the base a is equal to log of x2 base a, then x1 is equal to x2. Okay, so really similar to the one-to-one property of the exponential, right? So then how can you let's see an application of this one is example 6. So okay, so let's see problem D. Okay, so e to the x minus 1 is equal to 9. All right, so yeah, actually, I mean, so you may try you may try to apply the one-to-one property exponential because there is no log expression involved in this equation, but actually we cannot use one-to-one property of exponential because see on the right hand side there is no way to express 9 as e to the something. Okay, so then we're gonna use a log. What are you gonna do? First one, we take the natural log on both sides. Okay, okay, because how come? I mean, take natural log. Okay, so here, if these two guys are equal, then log of this guy must be equal to log of that guy with the same base. Okay, that's the one-to-one property of logarithm. So take a natural log. Why do we take a natural log? Because if we take a natural log, I mean log with base e, the left-hand side turns out to be just x minus 1. I will show you why. Because e to the x minus 1 is equal to natural log of 9. The actually natural log is what? Log with the base e, right? And then by the, see that log, the first one, we can take out n out of log. So we take out x minus 1 out of the natural log, the ln e. Since ln e is what? Log of e to the base e. So by the second law, that is turns out to be 1, right? So this is a natural log 9. So now x is what? 1 plus natural log 9. Okay? And then still you don't get it, right? I mean, what's the natural log 9? We don't get it. So it's okay. The natural log can be figured out the decimal expression using calculator. Okay? So right here, answer. I mean, the answer is what? 1 plus natural log 9 is approximately 3.1, 3.2. Okay? So this is approximately 3.2. Okay? This is how to use a quantum power natural log. Okay? So the other one is, C. 3 to the x power is equal to 50. Yeah, we take a log to the base 3. Now you see that why we take a natural log, a log to the base 3, because once we take out x, then log 3 to the base 3 is going to be 1. Log of 50 to the base 3, by the way, okay? So we got x log of 3 to the base 3 is equal to log of 50 to the base 3. This is 1. Right? So x equals what? Log of 50 to the base 3. So log of 50 is here log of 50. Okay, but here in the calculator, that log in TI series, log is common log. Okay, and then how can you figure out log 50? Yeah, you may just use other one, but one more thing is this. Give me a second. One more property is this. Log of a to the base b is equal to log of a to the base c over log of b to the base c. This is how to change the base. This is log with the base b, right? Can be, yeah, rewritten as the fraction form with the top and bottom ones is log with a different base c. Okay, that sometimes is useful. Okay, so this is equal to common log of 50 over common log of 3. Okay, so okay, so this is what? Log of 50 divided by log of 3. So approximately 3.56. Okay. All right. Okay. So let me stop here. Okay. So I'm gonna